I can do that.
You can tell us about yourself?
No, I skipped that part and get right into it.
Oh, yeah. Well, jump up on stage. I'll read it real quick here. We're going to move on to Dick Bourne. Dick is a semi-retired, it's in quotes, semi-retired engineer-inventor with a passion for energy efficiency. He played a key role for 25 years in Davis Energy Group's product development work and left that group to form the Western Cooling Efficiency Center in 2006. He retired in 2009 and later joined the integrated company to assist with emerging technology products. Please help me introduce Dick Bourne.
Hey, Sam, you want to give me a pointer on the pointer here?
That advances and that retracts.
Okay.
And that little dot up there is a laser if you want to use the pointer.
Little dot. Oh, yeah. Okay, great. Well, there's a lot of passion in this room today, and I didn't realize there was going to be so much, so I put that word in the intro that I sent on ahead. And I think that passion is really important to going forward. It's been a thrill so far to see how many people are committed to doing the right thing here. And sometimes that right thing is cost effective, and even when it isn't, it usually is the right thing for the long run. But I'm excited about being able to show you, actually I have two separate presentations here because I was given a little more time in the original schedule, and what we're trying to decide here is whether I do one now and then everybody eats. That's probably the best idea. And then I either do the second one over lunch or right after we eat. But in the first one, I get to talk about my home. Several people have done that already. But five and a half years ago, my wife and I, and we share the passion for energy efficiency, I think that'll show up in this project, decided that we lived out in the suburbs long enough and we wanted to move to downtown Davis. I don't know, how many of you have been to Davis? It's a pretty nice university community, and the downtown is really a vibrant place now, unlike 30 years ago. So we just found that we were spending more and more time downtown, riding our bikes downtown mostly. Bruce, I've ridden as many miles as you have, by the way, because I was a bicycle commuter since 1971 and taken some long touring trips too. But anyway, we decided we wanted to move downtown. We had built a very energy efficient house out in the suburbs of Davis 20 years before, got quite a bit of publicity for it. It was pretty near net zero energy. It cost us about $3 a month to cool it in the summertime without compressors. It was cooler than our neighbors' houses. And so we had learned some things that we wanted to take downtown if we could. And as we looked around at what was available, there weren't very many choices. But we got lucky and we found a piece of property a half a block from Central Park that has good open sky conditions, not too many big trees nearby, and was basically oriented east-west. It was a corner lot. And we fairly quickly found three other senior couples who were interested in retiring downtown like we were. And so we built a senior project called Parkview Place. And what I'm really emphasizing in what I'm presenting today is the geothermal aspect of it. There are a lot of really interesting and innovative aspects to this project, not the least of which was the social experiment involved. But I like the title of this overall program, Creating ZNE Buildings with Off-the-Shelf Technologies, because what we did was take a technology that Davis Energy Group, where I was for so many years, developed in the late 90s and really put on the shelf, didn't do much with, which is this GeoHelix ground-coupled heat pump technology. So now if I can advance, this is our building. We've lived in it for a year and a half now, almost. This isn't the most flattering picture of it, but I use this one because you'll see what was there before. Basically, I'm just giving you a list of what I'm going to try to cover in this first half, which I'm going to get through by 5 of 12, I hope. So briefly, the social experiment aspect of it, which is about 8 seniors coming together, pretty much, fixed in our ways and working together to build a building. And it's been very successful, I want to say. A little bit about the project, then I'm going to talk about the energy systems, the ways that we can integrate features in a building to really save energy and enhance comfort. A little bit about the GeoHelix installation, and then I'm going to talk about costs and cost effectiveness, because I think it's possible to build very cost-effective building. I should be pointing at that, I guess, huh? Anyway, to begin with, it's been a senior social experiment. This house was the Pena house, and the city of Davis, Narcissa Pena, who was the last of the Penas living in Northern California, at least in Davis area. If you've ever driven I-80 from San Francisco to Sacramento, you go by the Pena Adobe. It's a historic spot near Vacaville. That's the family that was so crucial in developing and occupying and farming a lot of Northern California, or at least this stretch. They had a Davis component. The last of the Penas, Narcissa Pena, lived in this house her whole life in downtown Davis, corner of 4th and D, and she died in 2008. The property came up for sale, and the question was, is there historic value here? Should this become a museum? Well, the house had no foundations, and it couldn't be saved, but conventional developers stayed away from it. And so we, with our group, were able to buy it, which we wouldn't have been able to if it had been an empty lot, probably. And we spent a long time deciding how we were going to do this project, how to organize. We became a community apartment project because that organizational mode is one of those that allows you to carry your former property tax valuation forward so that you don't get zapped with the full price of the new place you're building. It took us 4.5 years to actually get the building built, and the first occupants moved in well, actually 3 of the 4 couples moved in before the end of 2013. We make all our decisions by consensus, which is a very interesting process, but I won't say more about that now. We don't have the time. Summary on the project, we made a commitment to have this be a true net zero energy building from the beginning. We wanted it to be all electric because we couldn't figure out how to push gas back into the pipeline. So we made that commitment. We wanted to use the geo-exchange heating because, as Paul has pointed out, you can reduce the size of the renewable system you need if you use maximum energy efficiency in the building. So we developed a very good building shell. I'm not going to talk too much about that today, though, but that was the real focus. We have active solar water heating. We have a 11,000-gallon rainwater tank under the building, and we designed to be able to use the gray water to improve the performance of the geosystem in the boreholes. Well, we don't have that yet, but that's another story I better not tell. We had this fancy chart made that shows all the systems in the building, and if you come up here really close, you still can't read the writing there. But I just want to show that we have these various circles defining the different systems in the building, and the biggest one is the building itself. So we really focused on passive solar design of the building and on radiant heating and cooling. So all the heating and cooling, there's no forced air, all the heating and cooling in the building is from the floors. It's a very high quality building. It's a luxury building, really, with very classy tile floors. We built the building for $180 a square foot, though. And the other circle that I want to point to here is the geo system, which basically powers the heating and cooling of the building through the radiant floors. So that's enough about those circles. We have 7,600 square feet of occupied space in the building. This is the mechanical room. It's about the size of the furnace in a normal home. And if you put together the furnace and the outdoor, the furnace and the condensing unit in a normal home, our equipment occupies less space, and we're serving 5 apartments. We have the 4 owner-occupied apartments, and then we have a rental apartment on the first floor, which probably will house our caregiver within not too many years. But the geo-exchange system, we have 14 working geohelix boreholes. They're 24-inch diameter, 22-foot deep. Inside each of those, there's a spiral with half-inch HDPE tubing on about 6-inch spacing all the way down to the bottom. We have 2 40 kBtu, just under 7 tons of water-to-water heat pumps stacked. There are 2 units there. You're seeing one on top of the other. We don't have these superheaters in them. we use the upper heat pump as our auxiliary water heating source, and each of the apartments has two thermostatically controlled zones in it. The water heating is just like another zone, but it can operate in heating mode all year. And so that's the Geo system. Here's the most attractive view of the building, and we've gotten rave reviews really in town, is from the street, and you're seeing it really from the southeast corner here in this bird's eye view. But it is a 3-story building. It's flat roof, and part of our goal here was not to have the building be too tall, because it's just about the same height as a couple of tall 2-story buildings that are within a half block of it. And we had many struggles getting through the planning process with this building, despite the fact that it should be just what downtown urban areas are looking for today. But we did get through it. And you can see that on the roof we have flat PV arrays, 2 of them, one on each side. Each of those is 32 sun power panels, and there's a separate inverter for each of those sides. And then you can see our solar thermal 3-panel array tilted in the middle there. And there's only 75 square feet of solar thermal, but from early February through almost the end of November, we have all the hot water we need from those panels. And then we just have to supplement with the heat pump. Here's some shots of the assembly of the Geo Helix. We built a jig at the Integrated Comfort Shop in Vacaville and rolled these things up there. The tubes are held together in a pattern with oops, didn't mean to do that, back, with, didn't go back, with face-to-face tape, basically. And so you can see one of the tape strands being built there, and then they're pulled off the jig and they ship in a small pack. And you can see these bullseyes are where the drill's going to hit. The auger's going to hit there and drill the holes. And these are the completed Geo Helixes ready to go into the hole. And then here are 3 shots showing we've put the first row along the south side of the building. They were within 5 feet of the neighbor's fence. And here's the auger that drilled those. In the second phase, this was just a backhoe type rig that could put an auger on it. He had a bucket on the front, 24-inch auger here, which went down 13 feet before lunch for all the holes. And then after lunch, he put this 18-inch section on top, which is just a spacer, and allowed him to take the 24-inch auger all the way down to the bottom. Here's the support rig. These are the original design that we developed at Davis Energy Group, which is a suspender design. I'll show you a little bit more of that in the second half of the presentation. And so that's supporting it for backfill, and then the suspenders are taken loose after the sand fill is completed. And these are just some of the connecting tubes from bores that have already been completed down the line. So that's the suspender design. The last 4 coils, which we put along the east side, were done later after the slab for the building was in place. And we used we had a driller come out from Sacramento who had a much bigger rig that could go, he could auger a 40-foot deep hole with this thing. And here, by this time we had gone to the pre-stretched design that we expect to market. So you can see these guys are all, there's 3 of them here anyway. I guess 1 is already in the hole at this point. But these are stretched out, and they'll go in the hole next. And I'll show you a little bit more about that in the second part of the presentation here. But basically, this is just the first winter. We moved into the building in December, and the building was cold when we started, and it was a pretty cold month. And we had the loops filled with water, and we had inlet water coming in at 55 at the start, and dropped to 45, and the outlet from the heat pumps dropped to 32. And during that time, we were operating still with a COP that was pretty well up there. But by January, it was cold and dry, and not having the ground wet, we had hoped that we would be souping these up a little bit with gray water, and we weren't allowed to put our gray water into the ground. So I had us add antifreeze to the system, and outlet temperature from the heat pump fell to 26 degrees, and consequently the COP fell, but still that's a pretty high COP. By February, it was coming up again, and by March, we were back up almost to a COP of 5. So very, very efficient operation. Since that time, we've been through the first full summer of cooling, and we operated the system pre-peak. We never operated the heat pumps in the utility on-peak period during last summer. And we just pre-cooled we have 2-inch toppings, so it's wood frame construction, but we have our tubing in 2-inch gypcrete topping on the floors, and we would cool the apartments to 74. On the hottest days, they'd host up to 78 by 7 p.m., and then the heat pump was allowed to operate again. So and real comfort. The cool floor is really, really valuable for comfort. Just as in the winter, the warm floor is really wonderful. This past winter was the driest on record. There was almost no water flowing into the boreholes. Our drain water from the roof goes into the boreholes as well, by the way, after it fills the rainwater tank. And the coolest we had return water going in that I saw was 33. So we really didn't need the antifreeze that is still in there. Installed costs. Our installed costs were actually lower than this because there was some sweat equity involved. So what I did was to take our costs and I added a 20% margin for extra for labor, and then another 20% for a contractor margin. We used high density polyethylene instead of PEX for our floor tubing because the heat pumps are never going to get the water hot enough to exceed the rating on the HDPE. Half-inch HDPE you can buy in quantity for under 15 cents a lineal foot. So we got our full radiant system, including the heat pumps, circulating pumps on both sides, and manifolds with tubing on 6-inch center in for under $3 a square foot. We got it in for a lot less than that, by the way, because we actually got the tax credit applied for the ground loops and the radiant together. Our ground loops we got in for $1.12 a square foot, and our PV, I didn't leave the credit in that we actually took because it's no longer available on these. Hopefully it'll come back, but there was a Federal Recovery Act credit that applied to Geo through 2013 or 14, I can't remember which. But I left the credit in because it's still there for PV. So we paid $647 a square foot for our photovoltaic. Our total cost for these components was $1041. I conservatively estimated in this cost chart that the conventional HVAC system would have been $4 a square foot. And this is how we came out. We generated 27,500 kilowatt hours from our PV system. We used in the building less than 23. We had a surplus of 4,600, which we kindly sold back to PG&E for 4.5 cents a kilowatt hour. But it's reducing our meter charges for the 7 meters that were enforced on us. And so based on Title 24, our annual energy cost for the building would have been about 4,800. I took a 15 cent per kWh value for the credit for the excess PV. We need a Tesla, but nobody wants to buy it. So pushed the wrong thing again. Can I go back? So anyway, the bottom line is that we not only came out significantly net positive in our first year, but we have a payback that shows to be about 8.8 years, and that leaves out a lot of things. It didn't show any credit for not having to run any gas into the building at all. It doesn't show anything for the value of the increased value of the building for having these features, which is the thing that's a little silly about all the simple payback calculations that we do with buildings is that we neglect to consider the increase in value for the features that are being considered. We want them to go to zero value at a certain time as though they don't allow us to sell the property for a higher price because of their benefits. So anyway, I'm going to save the second half. What do you think? I mean, the food's here. So, I think we should all you know, belly up to the food bar here, and I'm happy to start talking early because I know there's a constraint. The next speaker is at
We have 20
Cornell.
minutes that we found, so
Okay,
we'll be good.
great. And for the next half, I'm going to put my necktie on because I'm more in sales mode for integrated comfort to get people excited about GeoHelix.
There we go. Great. Thanks, Dick, and we'll rejoin the Dick in a minute. That being said, lunch is served. Sponsors all around the walls, feel free to talk to any and all of us, please, and we'll rejoin in about 20, 25 minutes.
That's when we really achieve some success, is when we can get these technologies into production homes. So quickly, you're familiar, I think, with the traditional ground exchanger alternatives.
You can click it back.
Well, good. I should go by this quickly because it's just review. There's the deep bore vertical technology that's commonly used and particularly valuable where there isn't so much land area. You take advantage of deep earth instead of surface earth, and there are differences in performance there. And then the lower picture here shows the slinky approach that's like what Bill did at his house, where you have the land available to do that. And then the directional drilling approach that Bruce mentioned and showed a little bit about with, I think Ditch Witch developed that technology originally. So those are the traditional alternatives. And GeoHelix is a little bit different. It was actually pioneered, the first version of it that I saw was done by a fellow named Larry Marchiniak in Sacramento area, and he built these rebar cages and wired HDPE tubing around them and sunk them into augured holes. Pretty laborious, but they work pretty well. Meanwhile, Davis Energy Group developed this suspender helix in the course of a major project that we had, and I think that might be where I met Paul originally. I'm not sure, but it goes back 16 years or so. And we did a couple of projects with that, but the second one, we did a total of 36 boreholes as that next, and I'm calling that GeoHelix 1. It was the suspender design. It was used on a major multifamily project on the UC Davis campus, but right early on when the auger went into the ground, it hit an underground stream bed. And one of the constraints is you have to have soil that'll hold together so you can drill a hole of a given diameter and not have the sides just cave in on you. And that's what happened there. So that's pretty much when it went on the shelf. By the way, just a funny note is that when I did a patent search recently, someone in Italy patented our suspender design that we had demonstrated and documented for the Energy Commission 8 years earlier, and it got a patent in Italy. So good for them. And this is basically how it worked. You would have that pre-assembled helix like the one I showed, and then you would, so it's in kind of a tight pack, and then you put, after you auger the hole, you put this frame on top and connect the suspenders for the helix to that frame, and then cut the cords, and whoop, it goes to the bottom. Well, almost to the bottom, and that's one of the problems with the suspender design is that it doesn't always hit the bottom, and then when you backfill on it, you have a lot of stress on the tubes because it's all hanging from that top. So based on, and as I think I said about our project, the first 2 boreholes that we put in, we didn't remember the backfill protocol well enough, and we damaged them. So of our first 12, we only have 10 working. And by the way, on our project, we have 14 working boreholes for 7 tons of heat pump. So it's 2 coils per ton. So anyway, again, the suspenders, which in these original ones, there were 4 at quarter points, were taped face to face. So they do a really good job of keeping the tube in place. That's the advantage of having so much adhesive in there. So the second concept that we're using now, which we feel is really marketable, assembles them the same way, but it includes some clips at the top and about every 4 feet along the sides of the spiral that a 20-foot long half-inch PVC tube fits into and stretches the thing to full length before you put it in the hole. And then when you drop it into the hole, it hits bottom. And as long as you're backfilling through a section of chain link fence or some suitable screen so that you don't have big chunks falling on it, then you can backfill, and sand is best because it compacts so quickly. But you can, as long as you have that grade on top, you won't damage the helix. I think, and so these are very similar dimensional characteristics to what, except that those geohelix ones, those were in 3-foot diameter holes. We sharpened our pencils a little and figured out that the 2-foot diameter hole is a lot more economical in terms of drilling them and filling them, and probably that the difference in the amount of earth that you capture in the middle of the cylinder is not so great. It's you're mostly trying to make contact with the further away ground. So I think that was a good decision on our part. But these can, by the way, this configuration, unlike the suspender, can also be placed in horizontal trenches, and you get much more efficient use of the tubing than you do with slinkies because you don't have the interference. And I'm going to mention interference a little bit more later on, but I'm talking about thermal interference where you have tubes next to tubes. It's a problem with conventional vertical bores, by the way, because you may go 200 foot deep, but in the top 50 feet, you have your down tube and your up tube within a few inches of each other, and you're transferring heat directly from one to the other, and it's self-defeating. So what you'd like to do is have the water proceed continuously through the tube in a way that it's not in very close contact with the down tube. That's just from the thermal standpoint. Also, I'll get into some of this in pros and cons, and I better watch the time. The application range, the most important thing limiting us is that you have to have soil that can be augured. So if you're in rock or big gravel, forget it. Looking at the difference between, I guess I should just say that the characteristics of the geohelix are somewhere between the horizontal and the deep bore. The deep bore has the advantage that you're getting down usually into the water table, and you're getting down there to deep earth where the temperatures presumably are more stable. But on the other hand, you don't have access to the recovery characteristic that the surface earth gives you. So if you're in a heating dominated or a cooling dominated situation instead of a balanced situation, there are data that show that over time you swing the clump of earth that you've captured in a direction, and it just keeps going, and you don't have the long-term annual ground temperature working for you anymore. If you're heating only, it's cooler, and so you're losing efficiency. But compared to horizontal, you also capture more earth because you're basically taking advantage of the top 30 feet or so of the ground instead of the top 10 feet or so. But like the horizontals, you have the advantage of smaller excavation equipment. I don't think you rival the equipment advantage that you have, though, with directional drilling, where you can be out in the street effectively and go in. And if you don't have to be in the backyard too, that's a pretty neat option, and maybe it's as good or better an option for a retrofit. Anyway, the real pros of the geohelix are that you have less interference. This is interference here, okay? This guy's pushing this ball uphill, and this guy's not helping. He's resisting, and that's what I mean by interference, where you have tubes too close to tubes, and so you're losing the value of that part of your heat exchanger. The other thing that we do is use smaller tubing, which is more conductive, more shorter runs in parallel, therefore higher velocity flow in the tubing, and that contributes to better heat transfer. We also space them closer. We're recommending 8-foot spacing or so, and the deep bores you usually put on 20-foot spacing. So we're not asking heat to travel from as far away to get to our heat exchanger. Lower cost, faster installation is a main attractive feature of the geohelix. Also, we're above some of the barriers in the ground that water agencies are worried about penetrating. So if you can stay above that 25-foot level, you're less likely to allow surface contaminants to flow down through your hole and into the deep ground where it can contaminate the long-term water sources. And also, it's adaptable to retrofits in smaller sites, much more so than the deep bores. The biggest con is really rocky ground, but also you have less access to the deep earth, which if it's a balanced load situation may be a loss. We do see lots of ways to get them wet, even though our dry weather lately has not contributed. But another major disadvantage for people considering using it now is it's new. We don't have a lot of performance data, but we're pretty confident based on our experience so far with our project and on the two completed projects from last time around that it performs well compared to the alternatives. Rules of thumb, that there was some fairly detailed testing done back in the 1999 era on GeoHelix 1, and the conclusion was that one 20-foot deep bore was performed equivalently to 87 feet of deep bore. So we have a lot more pipe, of course, in contact with earth in our 20 feet. And so at this point, for projects that are coming to us now, just to be conservative, we're recommending 2.5 bores per ton. As I said, at our house, we have 2 bores per ton. It's working fine. We'd rather err on the side of conservatism and higher performance right now. Spacing, we've got about 250 feet of half-inch HDPE tube per coil, and we're recommending spacing the boreholes at 8 to 9 feet. Some of the synergies, keeping boreholes wet. If you can send storm drainage and gray water in there, that's going to improve performance. One of our synergies is combination with radiant floors, but this is a synergy that's there for all geosystems. If you have a smaller temperature range across the heat pump cycle, if you are delivering through radiant tubing than you do through forced air, so you just get better efficiency that way. We have excess solar heat from our water heating much of the year, and we're able to discharge that into our borehole field. And since we're heating dominated, that's beneficial for us. That's the Honda house that Michael's going to talk about. So that's the other job that's been done recently with our GeoHelix. Looking at equipment, I think you wanted to, if you're doing a small job, you want a piece of equipment like this. If you're doing a large job, you want a big rig like the one that I showed doing the 4 east bores at our project. It can go faster and have a separate piece of excavating equipment that's going to do the trenching and filling to connect the holes. Target cost per ton, I don't want to take more time, but I think these are pretty good costs for a near-term project where you've got 100 boreholes in a new tract home development. I think, $700 a ton range is possible if you're taking a less conservative approach and putting in 2 boreholes per ton. Otherwise, if you do 2.5, you're, a little bit more than that. So the status of the GeoHelix as a product, they're available now. They're in the field performing well. I'd say we're on a good learning curve. The economics are really promising, and I think it provides a really attractive way to get to cost-effective, true net zero energy in the relatively near future. So I'm happy to take questions if there's time.
Any questions, both online?
Bill, let's take yours while we're checking online.
Could you describe the nature of the sand if you would prefer specifications of your backfill?
Any sand is good. I mean, there are very few sands. The advantage of sand is there are multiple advantages actually. I mean, it's the least dangerous for damaging tubing in the backfill process. It's a wonderful filter. So in the face of any local agencies who are concerned about surface contaminants getting down through your borehole into the deeper earth. We're not going that deep, first of all, but second of all, the sand is a filter. And it compacts quickly. So I think if you use just cuttings from the hole and make sure that you put them back in through a grate so that they don't damage the helix, what you're going to find typically is if you don't do something to try to, something physical to compact it, within a year, you're probably going to have a foot-deep divot because there's going to be that much settlement. Whereas either sand or a good mix of sand and cuttings will give you very little long-term settlement in that borehole.
You ever use some, high volumes of water on filling the sand to really kind of slurry it in?
We haven't done that. I can see some advantage to that. Probably not in our current drought conditions, but water is so precious, but it might be valuable. We haven't found a need for it, but it could streamline backfilling. Yes.
Do you see any unbalanced manner of do you see any change in performance over time as the soil and stuff?
Well, unfortunately, there hasn't been a lot of data. The big project that was done, where I mentioned that we hit an underground stream bed basically, and there was a lot of gravel. That project, we did manage to get that. There were 27 boreholes for that one building, and it's been operating fine since 1999. So, and it's UCD campus. I don't know how routinely it's been occupied in the summer, so I can't speak to the load balance. Our building hasn't been finished long enough to speak to it much either, except that we are clearly heating dominated, and we've had higher ground temperatures this winter than we had in the first winter when we had that big early drawdown. So, time will tell.
Has this been used for cooling?
Yes, I mean, we have used it for cooling. In all the projects that it's been installed in so far, which is 4, it's been used reversibly for heating and cooling. But the question is, what's the balance, what's the annual balance? And the monitoring probably hasn't been sophisticated enough to let us answer that. Okay?
Great. Thank you, Dick.
Thank you.